less people the last hour. For sure, I think we should make only one break from now on because we don't respect the break. We made 2 breaks, which are as long as one break. So next time we'll make 1 break. Unless you promise me that you will stop just for 10 minutes. If late, then Mark Herbster has to teach in 2 weeks. So we need to cover his material. So let's try to be more precise. Okay? So, any questions? No?
Yes,
yes.
sorry, function 5, you said when we, it's written somewhere when we choose the function following appropriate. Can you elaborate on that?
Which slide? Which number?
No, 75.
Yeah. So, right, so, so let's quickly summarize all the points of the lecture so far for today. We've seen how to replace least squares, so empirical minimization, with regularized version, rich regression, and we've seen that there are 2 ways to represent the solution. One is to solve it, order the 3-dimensional system of equations, directly. The other is to solve this dual linear system equation, which give us the vector alpha. Right? And we've seen that this is advantageous if the sample size is more than the function. Then we have applied exactly the same recipe to nonlinear function spaces. So in the case in which our regression function is a linear combination of some basis functions, which however themselves are nonlinear functions. And the prototypical example are polynomials. Right? So the components of the feature map, feature vector are monomials, second degree. And we have seen that in this case, which is not true for every choice of the feature map, in this case, the inner product between the 2 feature vectors does not need to know explicitly the feature map in order to be computed. It only needs to know the inner product between the 2 inputs. So this is true for some feature vectors. Right? So the key point is that if you choose your basis function, the feature vectors, appropriately, computing the kernel, which is all you need to make business work, right? To solve the linear system equation in the kernel matrix, to compute the function in the kernel. Right? So if phi is chosen appropriately, the kernel function does not depend explicitly on phi. It only depends on implicitly. So k of x and t, in order to be computed, you don't need to know at capital X, right? And you've seen that in this case, it is clear, right? So if you take this feature vector here, right, which are very high dimensional, right? These are all monomials of degree r. The inner product is obtained by taking the r power of the inner product of the inputs. So in this sense, the feature vector disappears. That's the trick. So, for certain choices of the feature vectors, the kernel can be computed. Computing the kernel is independent of n, understanding the feature space. So, this observation then leads us to the last topic, which is how can I detect when a function k is a kernel? So, when written as the inner product between two feature vectors. If that is the case, I can use this function to build my kernel-based methods. So I compute the coefficients alpha, and then I predict the output of x is a linear combination of the alpha times the kernel centered at the data. Centered at the data means k of x I, comma x. One of the two inputs is the point, the other a lot of words. And, you need to let it, how to say, sediment. But it is no more complex than that. You just need to think about it.
Yes. For functions to be polynomial, you also have to have I to be an integer.
Yes, absolutely. Yes. So, we don't have much time, and I don't want to. Okay. So we don't have too much time, and I'll skip some of the slides. But I want to show you some examples which are very important. So the general question that we want to ask is, for example, if you take p is a function, right? For which value of p is this occurring, right? So for which value of p, that p of x transpose t can be written as linear product between two feature vectors of x and t. And more generally, the other question you could ask, you have a kernel, right? This is a valid kernel, and for which function p, so this is a different function, it's a univariate, right? Here is function, sorry, you will say, for which value of the function p, for which function p, this is still a kernel. So k is a kernel, when is p of k is still a kernel. So, so we need to verify that this function p has the property that when we choose our data points, wherever they are, the induced matrix is called semi-definite. And so here the answer is that if p is polynomial with no negative coefficient, this is a kernel. We will see some examples. So these kind of questions are, you can ask many of these kind of questions, but let's try to be a bit more down to earth, and just two kernels, which are widely used in machine learning. So the first is a polynomial kernel, which I've written a little bit differently. There is also this parameter a. This is also called homogeneous polynomial kernel. So it is homogeneous. So if a is equal to 0 is the previous one. But if a must be a non-negative number, then the kernel is homogeneous in the sense that the underlying feature maps involves monomials of degree between 1 and up to r. Whereas for a equal to 0, where all of the same degree are. Okay? So this is kind of more general definition. So more generally, as I said, if the function p is a polynomial with non-negative coefficients, then p of x transpose x is a polynomial. Okay. That will be clear later on. Another example of a function k, which is a kernel, so it's points semi-definite, is the Gaussian. So this is very widely used. So you take k of x comma t to be essentially the exponential of a parameter beta minus beta is more than 0, times the square distance between x and t. Okay. And this is also a kernel, as we will see in a bit. However, this is an example of a kernel whose associated feature map is infinite dimensional. So, so this is quite general, and there are many questions one can ask. So going back to linear function, if I define the following function, right? So it's X transpose AT, so quadratic form. Now this is a kernel if A is a Poisson semi-definite. And the proof is here. Kind of left as an exercise, but again, use the fact that if A is Poisson semi-definite matrix, then you can write it as a matrix R times R transpose. Right? So you can take a square root of A, and then you see that if you take your data points, x1 through xm, right? So this sum goes from 1 to m, the quadratic form is always more or equal to 0, right? And you use the fact that, and this is the feature map, R transpose X. So this example is kind of the general linear curve, right? So ridge regression uses the case in which A is the identity, right? So the kernel is just X transpose X. That's the simplest possible kernel. In general, if A is Poisson semi-definite, this is still a valid kernel, and it is linear. So linear in the sense that the feature map is a linear mapping. Right? Map the input space to another space for a linear transformation, whereas the polynomial kernel involves a linear transformation, right? Features of higher degree. So here is the proof. Then this might be a little bit confusing, but now, if you know that, now suppose that you prove that capital K is a kernel, right? So, for example, we know that the linear kernel, X transpose T, is a kernel, or we know that X transpose T to the power of R, we saw it in the previous hour, is a kernel. Now you could ask the question, if I form another kernel, K tilde, and that K tilde of X comma T is K of phi of X comma phi of T. Now here, what is confusing here that this phi is another feature map. So perhaps we could have called this phi like this. Okay. This is a vector mapping, but it's not the previous one. Okay. So now in this case, K tilde is still a kernel. Okay. So basically, you can compose kernels and still have kernels. Is what this says. Right? And so this looks a bit complicated, but why I mention this? Because this gives you another way to prove the previous result. So if you take K to be the default standard linear kernels, X transpose T, and you take phi to be a linear transformation, so it's R transpose X, then in this case, K tilde is the general linear kernel. So it's right? So in this case, K tilde xt, you get X transpose R transpose T, so it's X transpose A T. A is Poisson semi-definite. So you can ask even more general questions. I'll skip this. So you can ask, so one way to build a richer kernel function, and you start from some kernel that you know, simple kernels, and then like you know that K1 through KQ are kernels, and then you ask which function of these kernels still gives me a kernel, right? And the idea, the more you combine this kernel, the richer it becomes the feature space, the underlying feature space. So the more complex and expressive the underlying model will be. Right? But you can answer these questions, right? And let's see just some important cases. So in general, a non-negative combination of kernels is a kernel. This is kind of obvious, right? Because if you take matrices which are Poisson semi-definite, the negative combination remains Poisson semi-definite.
Excuse me?
Yeah, so in a negative combination of kernels, it's still a kernel. So for example, if you multiply a kernel by a number which is a negative, it's a kernel. or if you take the sum of two kernels, it's still a kernel.
But when you say you're going to skip, are you going to get back to it later?
No, it's just there for your.
So we don't need to know it.
I guess not. Yeah.
We don't need.
For the example,
Can you-
if you want to do research, perhaps it's important. So, the sum is a kernel, the product by the scalar is a kernel. Now, what is more interesting, this is less obvious. If you take the product, the element-wise product of two kernels, it's still a kernel. Right? So, if K of S comma T is the product of K1 and K2 at X comma T, that is still a kernel. Okay. This also is again, this is useful, right? Because if I take K1 equal to K2, for example, in the linear kernel, I get my polynomial of second degree kernel. So this is another way to prove that that's the kernel. And this is an interesting and useful exercise to do. Right? So to realize, to prove that, again, no matter which inputs you choose, the ground matrix associated with capital K is polysemi-definite. If the ground matrix of K1 and K2 are polysemi-definite. And this is an example in which the proof follows from kind of brute force. You just use, I don't have time to do it in detail, but let me give you some hint, right? So, so what you need to show is that you take your inputs, right, and you form two matrices. The first is the gram matrix of K1, and the second is the gram matrix of K2. I call this A and B, right? So what you need to show is that the matrix C, which is obtained by taking the element-wise product from A and B, this is what the product of kernel does, right? You need to show that this matrix is polysemi-definite, so it's more or equal to 0. And the way to do it is to use the eigenvalue decomposition of A and B, which exists because A and B are polysemi-definite, and you plug it there, right? Right? So Cij is equal to Aij, which is this, times Bij, which is this. And then you move sums around, and you arrive at this conclusion. So this is a very useful exercise to do. So I think we've already seen 2 or 3 exercises to do so far, and I hope you have taken note. It's very useful to do these things. And next week, if you have time, we can discuss them. Okay. If they're not clear, we can go for the digits. So, in summary, so what I really wanted to get to is that the summary is that there are some algebraic properties which preserve function K to be a kernel. So the kernels, and I sum them up, I have a kernel. If I multiply by positive number, I have a kernel. If I multiply them to kernels, I still have a kernel. And if I use this composition, I still have a kernel. Okay? So through this property, we can build a very rich family of kernels. And so what is interesting, for example, going back to polynomial kernels, we can build kernels of this type, right? And again, a typical example, just think of AXT is X times T, right? And so, in particular, if I choose my coefficients AI, right, this way, right, AI to the power of, sorry, AI, right, so as we said, some point to be AI. This is a kernel, AI is 0. So here I choose AI to be a number, a negative, the power of I divided by I factorial. Well, then you know that I think this should be R. This is a typo. So R is the degree. Okay, so then you know that if you take the sum, right? And we let R go to infinity. So, the previous. Yeah, so.
Also, I know the one where you make the additional notes.
Which one?
Yeah.
Yeah. Well, let me remake the notes on this slide. Okay. So all you have here is what I have. So we've said that this is a kernel. If AI are more or equal than 0. And then I choose, as an example, AI to be A, which is a negative number, to the power of I divided I factorial. I factorial is the product of all the integers starting from I in the increasing order. Then you know from calculus that this this sum, as R goes to infinity, converges to the exponential. Right? So as R goes to infinity, this is equal to the exponential of A times x equals t. So this is still a kernel, right? Because for every value of R, this guy is a kernel, so the limit will also be a kernel. So this function is still positive identical. So if I take my inputs wherever they are, from the gram matrix, it's positive identical. And this is the first example that we see in which the underlying feature map, so given a kernel, there is an underlying feature map. And when I write it down explicitly, the underlying feature map is infinite dimensional. So if I do linear regression using this kernel, and it's too soon to discuss later, but I can interpolate, I can go arbitrarily close to my data points, no matter how many they are. So that the function space, is the model induced by such a kernel is so rich that no matter which data points you give me, right? So for example, it could be completely random, it could be completely noise. I can find a function which goes through the point if I choose this guy here. Whereas if I choose a polynomial kernel of degree R, at some point I cannot interpolate because if my function becomes too complex. I can only use a linear expansion of monomials of degree up to R. This has, although very rich, has a limited part. Right? So this is the first example in which we see that using these kernel methods, we can reach the method can learn, in principle, can learn everything. But here is the big question. Right? So in principle, it can learn everything. So if the data are generated, right? So there is God, let's say, who generates the data. So you give me an input, and God tells you what yi is. Perhaps plus a little noise, right? So let's make this experiment. Right? But you don't know how the output is generated. Right? But if the way it is generated involves a very complex function, it involves a polynomial of degree 2 millions, right? If I put there r equal to 2 millions, eventually I should get the function if I have enough data points. Okay. However, if the number of data points is very small, I might completely overfit the function. This you have seen last week with the this concept. But now, if I use this polynomial kernel, so it means that I can fit any function, so to speak. Right? So how is it possible that I can learn this function? Because I will always have a finite number of points. So this is perhaps the big question of the course. How is it possible that I can? This is a statistical question. Okay? How is it possible? But it is also an approximation question. So how is it possible that using a feature space which is infinite dimensional, because this is the feature space induced by such infinite polynomial kernel, how is it possible that this stuff works? So I can learn this unknown function that God knows, but I don't know. I only know the data, which are finite numbers. How is it possible that I can catch that function? Well, the answer is difficult to provide, but informally speaking, an important point is that yes, this kernel has an underlying infinite dimensional feature space. But if you go inside your lens and look, what are these features? Here they are, right? So if x if the input is one dimension, these are the features. So the first is constant, because you can have a constant function. The first is linear in x, the second is quadratic, and so on. All the monomials of increasing degree. But look at here. Here you have also a coefficient in front of this basis function. Right? And this coefficient goes to 0 as the order or the monomial goes to infinity. So this means that even though I have an infinite number of basis functions, as the order of the monomial, as the complexity of the function decreases, the more I penalize the regularization, the corresponding coefficient, the basis expansion. So what happens is that here, through regularization, you can still catch the underlying function using this method. So you solve the linear system equation, you find alpha, and then you will find out if the underlying function that you don't know, God knows, is still a generic polynomial of arbitrary degree, but the coefficient decay sufficiently fast. So in a way, it is moved, the function is moved. This is what happens to polynomials when the coefficient decays sufficiently fast. And all this is informal, as I said. Then in that case, this stuff works if, there's another if you choose this regularization parameter, this tuning parameter appropriately. Okay. And now we see an example where we do this, and then we stop. And this we will repeat, so this last message is very dense. I think it's the most important lesson to learn from this method. So what we have seen today are some computational properties of these current methods, how we can represent nonlinear functions. But also what I've just mentioned now for the first time is that although we go to an infinite dimensional space, we penalize more and more the higher degree basis functions. And this is why this stuff somehow works. Right? So it regularizes more, the complex functions. And here, so one way to understand this stuff is to read the map. And another way, if you struggle with the map, is to, so to speak, make your hands dirty and implement some of these methods. Because one message of this lecture, implementing these methods is by no means possible. It's easy. You have to solve the linear system of equations, which is something that everybody does. So you can solve the linear system of equation and see what happens to your solution. Right? So using the training set and the validation set, as, for example, the sample size increases, as the regularization parameter varies. And here is what you see in this specific case of this curve. So here I take inputs in one dimension, and I take this parameter A equal to 1. So I take this curve, right? And it's actually a bit hard to see, but I have this data point. So here I have one data point. I think it should be clear from the notes, but it's not a good plot. So the best thing is to redo this plot in MATLAB. So you have two data points, input outputs, and then you try to solve the ridge regression, the regularized ridge regression with this kernel for different values of lambda. Right? And you see that as lambda if lambda is small, remember, if lambda is small, we minimize the error. We try to fit our function in the data. So if lambda is small, the function goes through the points very much. As lambda increases, my function is a polynomial, right? Of arbitrary degree, not exactly. My function becomes flatter and flatter, smoother and smoother. Right? So if lambda is 10 to the power of 3, so it's very large, the function is something like this. It's almost 0. So here this parameter lambda controls the smoothness, the shape of the function, the regularity. And lambda is the regularization parameter, so we minimize the error plus lambda, the norm of the coefficient factors. So this one on page 5 or 6 is our underlying algorithm, age regression. So page 7. So this is another useful exercise to do. I think you will do this in the other course. And one way to choose the regression parameter is to do cross-validation, although there are other methods. Let's say a natural method is to do cross-validation. So you, let's say you use a validation set, so you have additional data that you use only to monitor how the error of the function found in the training data, what the error is of the validation set. And then you see that the validation error should not be good. The validation error, which is this one, is first I, then it kind of goes down. Of course, this is kind of a real experiment. Things are not. It goes down, and then it goes up again. Right? So since you try to minimize, to find lambdas when the validation error is smallest, you choose this value of lambda. Right? In this case, this value of lambda also corresponds, also gives you a model which has a small test error. The test error is the dashed line. Validation error is possible to see that it's what I did. So in this case, you kind of catch that. Any questions? I see that there I understand everything.
From the example shown above, I would then choose the one that has the smallest error on up. Yeah, on the previous slide.
Yes, which one will, I don't know. Let's see. Looks like we choose the, looks like we choose the third one. Possible? I don't know. The best way is to do the experiment. It looks like the third one.
We have to minimize the all-out cross-validation error.
Yes, the one-out error. Did you discuss the one-out error last week? So in this case, you take 1 point out, you train all the others, and you test, and then you rotate. But you can just use a validation set to make it simple. So you take your training data, you take like 70% of them to train, and the 30% you keep it aside to test, to monitor this parameter line, to choose the best one. This is less, it's computationally more efficient. So, I think we are almost done. So, in time again. But there is more that one could say. So, for example, so we mentioned before the Gaussian kernel. but we kind of left it behind. So this is another example which is very interesting, in which you have a rich model, so infinite dimensional feature space. And so these Gaussian kernels are of a different kind. So they're not functions of the inner product between the inputs, but rather they are radial functions. So they are, the kernel is a function of the norm of x minus t, right? So of the distance between x and t. So these are other family of kernels where you see the Gaussian kernel. More generally, you can have what are called translation invariants. So there are kernels which are a function of x minus t. So this is more general than this. And the books, there are the results are developed which tells you under which condition these are kernels. So the condition here involves this function little h or the function capital H. Okay. So we don't see, so this is beyond the scope of the course, but it's just a pointer to tell you that there is a rich theory for deciding whether it is a Bible kernel or not. But in some cases, it is easy to see. So let's see at least the Gaussian kernel, and maybe also the periodic. So if you choose the Gaussian kernel, this is a kernel because you do some algebra and you see that it reduces to products of functions in all R kernels. So you span the exponent, right? And what do you get? You get x transpose x plus t transpose t, right? And then you get the cross product. And so, and you separate it, right? So you take the first part times the exponent of 2 beta x transpose t. So you get 2 beta because you have minus beta times minus 2, you get 2 beta. Right? I've just expanded the numerator of the argument of the exponential. Rearrange the terms. Now, this is a kernel because we saw before that this guy is a kernel. It's a point. It's what we have called the infinite polynomial. Right? And now you see that so this guy I can write it as phi of x, comma phi of t. Some feature map that I described before explicitly. But now, here what you have, the new term is just this one. Right? Just this term is new. But you can simply take the feature map that you have obtained for a polynomial kernel and multiply every component of this vector by this function, right? And then you still have the feature map. So this is a kernel. In fact, there's a simpler way to see it, which is the way which is described here. So this is a kernel, and this also you can show is a kernel. It's a very simple kernel. So, and we'll see that the product of two kernels is a kernel. So this is the simpler way to prove it. Okay? So the infinite polynomial is a kernel. And the first term is a kernel because simply it's a one-dimensional kernel in which the feature map for that kernel is just this function. It's one-dimensional. So, does it make sense?
Could you maybe point towards the slide where's the mechanism for proving what's a kernel and what's not?
There are different ways to prove if a function is a kernel.
Just because you said it's so simple.
No, there are different ways. Some might be to a difficult proof, some to a simple proof. In this specific case, there is a simple proof that this is a kernel if you use some facts that we have kind of mentioned before. And the fact to use is that if you take two kernels, the product of these two guys is still a kernel.
Yeah, I meant
Okay.
the new one.
Yes.
You mentioned also the new one.
So why is the new one a kernel? Right? Because it can be written as the inner product of the feature vector of x times the feature vector of t. And the feature vector is one-dimensional, and it is this guy. Right? So That's the way you prove it. So I really want to do this again because this is really this is one of these things that are so simple that it can be confusing. Okay, so what I'm saying is that this kernel, so this is x, and this is t and t. Right? So this is a function of x and t. This is a kernel, so it's a valid kernel, or it's my name, because I can rewrite it as a product of a function phi of x times a function phi of t.
Okay.
That's, in general, we have seen that a function is a kernel is the inner product between a feature map of x, the feature vector of x, and the feature vector of t. In case the vector is one-dimensional, and it is just this. So the Gaussian kernel is a kernel because it is a product of a very simple guy, kernel, and what before we have seen to be this infinite kernel. And this proof, there is a quick proof. It doesn't, it is not a constructive proof in the sense that you don't find a feature map. Maybe knowing the feature map is useful in order to interpret what are the underlying functions. And to do that, you so one way to do it, an exercise, is to go back to the infinite polynomial, write down the features. It's what I was trying to do before, then I got confused. You write down the feature map for the infinite polynomials, and then you need to modify, taking into account this guy here, but we just modify each component of the feature map by this function. So you can, as an exercise, you can derive explicitly what the features are in this case. So I think we have 4 more minutes. So so unfortunately, some of this stuff is a little bit technical, and I sympathize with it. As I said, but however, the reason for which we do all this is that this stuff is used. If you go down also to practical work, we use so kernel methods I would say are one of the off-the-shelf methods I use in machine learning. And if you want to use them, understanding something about why you use them and what is the meaning, what you are trying to do with some methods, you need to understand a little bit of the stuff. So you need to understand what can you represent, what can you approximate using a certain kernels, and can I use this kernel? Because if you try to train simple vector machines that maybe I've heard of, this week we will discuss that. If you use a kernel which doesn't satisfy this property, your algorithm will train forever. You're always there waiting on your desk and see, have I gotten my solution? Right? Maybe if you work in a company, they fire you because you are still waiting. So it's important to know a little bit of this stuff. But some of this stuff, if you want to know it well, it's also, so this stuff will not be in the exam, so to speak. Right? But it's important if you want to go a little bit beyond. Master this stuff. So, and this is very short. And so just a pointer to what you find in more details in books is the fact that if you take this translation invariance kernels, k of x minus y, so here the notation has changed. Before we call it t. So, and there are conditions on the function h which ensures that this is a kernel. Right? The conditions are written there. Conditions are that h is an even function. H of x is equal to h of minus x. And when you take the differentiable, then the Fourier coefficients are all negative, and the Fourier basis involves only the cosines, not sines. You need to have cosines because the function is even. So if the coefficients are non-negative of the cosines, you can, so in this case, the way you prove it's a kernel, you explicitly construct the feature map. And here, it's written here. So if you know Fourier series, you walk a bit through the slides, you will understand that function h, which is even and has negative coefficients, is induces a kernel. Right? And this is another example where you see that the induced feature space is infinite dimensional, and using such a kernel you can approximate a function. But again, this sum converges in series, so the coefficients an goes to 0 as n goes to infinity. So n is the frequency of the cosine. The higher the frequency, the more an, and the more you will penalize the corresponding features. So again, you can approximate the function, so this stuff, trying to put penalizes more, penalize more higher frequency. Yeah. So I think we will next week we will meet again here.